The Atlantic Ocean stretched dark and infinite beneath a moonless sky in the autumn of 1953. Far below the surface, beyond the reach of starlight and the eyes of surface vessels, a submarine moved through the water at a speed that defied every assumption about what was physically possible for a vessel operating submerged. USS Albacore, an experimental research submarine commissioned just months earlier, was carving a path through the deep at velocities that left Navy observers stunned and skeptical in equal measure. The dial readings showed 33 knots, faster than most World War II submarines could achieve on the surface burning maximum fuel, faster than the theoretical limits predicted by every traditional engineering model, faster than anything the United States Navy or any other naval power had ever recorded for underwater operations. The achievement wasn't just remarkable, it was revolutionary, and it would trigger a cascade of changes that would reshape submarine warfare across the globe and humiliate the Soviet Union's most confident naval engineers. For decades, submarine design had been constrained by assumptions rooted in surface warfare. Submarines were viewed primarily as surface vessels that could temporarily submerge for tactical advantage. Their hulls were optimized for speed above water, with long cylindrical shapes, flat decks, and sharp bows designed to cut through waves rather than water. When these vessels dove, they became slow, ungainly, and vulnerable, creeping through the depths at speeds that made them easy targets for destroyers and aircraft equipped with increasingly sophisticated sonar and depth charges. The entire doctrine of submarine warfare was built around stealth through slowness, hiding in the depths, and moving cautiously to avoid detection. Submarine captains knew that once detected, their only hope was to dive deep and move slowly, using the ocean's thermal layers and background noise to mask their presence, while they crept away at speeds barely faster than a walking man. But the Cold War had changed the calculus entirely. The Soviet Union was building submarines at an alarming rate, deploying boats across the Atlantic, Pacific, and Arctic oceans in numbers that threatened to overwhelm American naval defenses. Intelligence reports flooding into Washington painted an increasingly dire picture. Soviet submarine commanders were becoming bolder, their boats more capable, their tactics more aggressive. American admirals feared that in the event of war, Soviet submarines could establish a stranglehold on Atlantic shipping lanes, cutting off reinforcements to Europe and isolating American forces abroad. The old fleet submarines, heroes of World War II campaigns against Japanese shipping, were inadequate for the new threat environment. They were too slow, too loud, too limited in endurance. Something radical was needed. Not an incremental improvement on existing designs, but a fundamental reimagining of what a submarine could be. The answer came from an unlikely source, not from admirals or weapons designers, but from hydrodynamic engineers studying the shapes of fish and whales at the David Taylor Model Basin in Maryland. These researchers had spent years testing scale models in water tunnels, searching for hull forms that could move efficiently through water when fully submerged. They experimented with dozens of configurations: long hulls, short hulls, wide hulls, narrow hulls, shapes with fins and without, configurations that seemed elegant and others that looked absurd. The testing was painstaking and methodical, with each model evaluated across hundreds of different speed and angle combinations, while sensitive instruments measured drag, turbulence, pressure distribution, and flow patterns. Their conclusions challenged everything the Navy thought it knew about submarine design. The traditional long, narrow hull with its surface-optimized shape was, according to the data, one of the worst possible configurations for underwater speed and efficiency. The flat deck that allowed sailors to work topside when surfaced created enormous drag when submerged, acting like a brake that consumed power and limited speed. The sharp bow that cut efficiently through surface waves generated massive turbulence underwater, creating noise that could be detected for miles and vortices that increased resistance. Every feature designed to help a submarine operate on the surface, the deck gun mounts, the periscope fairings, the angular conning tower, worked against it beneath the waves, adding drag and creating acoustic signatures that betrayed the vessel's position. Nature, the engineers pointed out, had already solved this problem through millions of years of evolution. Whales, dolphins, tuna, marlin, creatures that spent their entire lives moving through water, had evolved a completely different shape through the relentless pressure of natural selection. Wide in the middle, tapering to points at both ends, smooth and streamlined, with no sharp angles or flat surfaces to create drag. The shape was called a teardrop, and according to the model basin tests, a submarine built with this configuration could move through water with dramatically less resistance, achieving higher speeds with less power and creating far less noise in the process. The reduction in drag wasn't marginal, it was transformative, potentially cutting resistance by 50% or more compared to conventional hulls. The theory was elegant and the data compelling, but implementing it would require the Navy to abandon decades of tradition and bet millions of dollars on a hull form that looked nothing like any submarine ever built. Skepticism was fierce and came from every level of the naval hierarchy. Senior officers who had commanded submarines in World War II argued that the teardrop shape was impractical, that it would be unstable in rough seas, difficult to control during rapid maneuvers, impossible to dock safely, and vulnerable to damage from even minor collisions. Design chiefs worried about the internal layout. How would crew spaces, machinery, and equipment fit inside a hull that was wide in the middle but tapered at both ends like a football? How would ballast tanks be arranged to maintain proper trim? Where would control surfaces attach? How would the propeller shaft run through a hull that came to a point at the stern? Shipyard managers questioned whether the design could even be built with existing tools and techniques, pointing out that the complex curves required precision forming and welding that pushed the limits of available technology. Congressional budget committees demanded to know why the Navy wanted to spend taxpayer money on what one particularly hostile legislator called a submarine shaped like a blimp, designed by people who apparently never served on a real boat. The political opposition was substantial enough that the entire project nearly died in committee, saved only by the intervention of a few influential senators, who understood that Soviet submarine expansion posed an existential threat that required bold responses. Even among the project's supporters, there was widespread doubt about whether the radical design would actually work. The model basin data was convincing, but models were not reality. Scaling up from carefully controlled laboratory conditions to a full-size submarine operating in the chaotic environment of the open ocean involved countless variables that couldn't be perfectly predicted. But a handful of visionaries pushed forward, convinced that the Soviet threat was real and growing, that incremental improvements to existing designs would never close the performance gap, and that bold innovation was the only path to maintaining American naval superiority. Captain Harry A. Jackson, who would become Albacore's first commanding officer, reviewed the model basin data and concluded that the potential benefits justified the risks. Admiral Charles B. Momsen, a legendary figure in submarine development who had invented the Momsen lung rescue device, threw his considerable influence behind the project. And crucially, some members of Admiral Hyman Rickover's nuclear submarine development team recognized that if the teardrop hull worked as promised, it would be the perfect platform for nuclear propulsion, combining unlimited underwater endurance with unprecedented speed. In 1952, after months of contentious debate and political maneuvering, Congress reluctantly authorized funding for a single experimental submarine, a vessel that would carry no weapons, participate in no combat operations, and exist solely to validate or disprove the teardrop hull concept through systematic testing. She would be called USS Albacore, designated AGSS 569, classified as a research submarine, and her mission would be to test whether the radical theories developed in model basins could actually work at full scale in the real ocean. The authorization came with strict conditions. The experimental program had a limited budget, a tight timeline, and explicit instructions that if the design proved unsuccessful, no additional teardrop submarines would be built. Construction began at Portsmouth Naval Shipyard in New Hampshire in 1952, and from the first day, workers knew they were building something unprecedented. Albacore's keel was laid on March 15th, and as the hull began to take shape, it became clear just how different this submarine would be. Her overall length was just 204 feet, short by submarine standards, but her beam at the widest point was 27 feet, giving her an almost tubby appearance compared to the sleek, elongated profiles of traditional boats. The hull plating had to be formed into complex compound curves that required special techniques and constant quality control to ensure proper strength and watertight integrity. Welders worked from detailed templates, forming each section with precision before joining them into the distinctive teardrop shape. Inside, every available space was crammed with instruments and experimental equipment. There were no torpedo tubes taking up valuable bow space, no weapons control systems, no combat information center with plotting tables and fire control computers. Instead, the interior was packed with sensors, data recorders, pressure gauges, acoustic monitors, hydrodynamic measurement devices, and miles of wiring connecting everything to central recording stations, where engineers would monitor and document every aspect of the submarine's performance. The battery compartment, normally designed simply to provide power, was instrumented to measure electrical consumption patterns with unprecedented precision. The engine room contained not just the diesel engines and electric motors that would propel the boat, but elaborate monitoring systems to track vibration, temperature, pressure, and efficiency across every operating condition. The crew spaces were cramped even by submarine standards, because so much interior volume was dedicated to test equipment rather than berthing and amenities. Bunks were stacked 3 high in some compartments. The galley was minimal. Storage for food and supplies was limited, restricting the length of missions. But the crew selected for Albacore's initial trials accepted these hardships as part of serving aboard an experimental platform. They were a carefully chosen mix of experienced chief petty officers who knew submarine operations inside and out, junior officers willing to take career risks on an unproven boat, and civilian engineers who would conduct the tests and analyze the data. Captain Jackson, Albacore's first commander, gathered his crew before the commissioning ceremony and told them honestly what they were undertaking. "We're not going to hunt enemy submarines or launch missiles," he said. "We're going to run the same speed trials over and over, execute identical maneuvers dozens of times while engineers adjust single variables and record results. It's going to be scientifically important work, but operationally monotonous. You won't get combat ribbons or medals for heroism, but if this design works, you'll have served on the boat that changed submarine warfare forever. And if it doesn't work, well, at least we'll have tried something bold instead of doing the same thing the same way and expecting different results." On August 5, 1953, USS Albacore was officially commissioned in a ceremony attended by Navy brass, politicians, and engineering teams who had spent years bringing the concept to reality. As the commission pennant was raised and Captain Jackson read his orders, observers noted the submarine's unusual appearance with a mix of curiosity and doubt. She looked strange, unconventional, almost comical compared to the sleek, traditional submarines moored nearby. Some officers made jokes about the pregnant whale or the floating potato. Others simply shook their heads, convinced the Navy had wasted millions on a boat that would prove to be an embarrassing failure. Initial sea trials began immediately, conducted in the waters off New Hampshire and Maine. The first runs were cautious, testing basic systems, verifying that the unusual hull could be controlled, ensuring that ballast tanks, diving planes, and rudders functioned as designed. Engineers were particularly concerned about stability. The teardrop shape concentrated most of the submarine's displacement in the middle of the hull, creating a center of buoyancy that was very different from traditional designs. If the calculations were wrong, Albacore might have a dangerous tendency to roll, making her difficult or impossible to control in certain sea states. But as the trials progressed, those fears proved unfounded. Albacore handled beautifully, responding to helm and dive plane commands with a precision and agility that surprised everyone aboard. She turned more tightly than conventional submarines, changed depth more rapidly, maintained trim more easily. The wide hull, far from creating stability problems, actually provided better roll damping than narrow traditional designs. After a week of basic handling tests, Captain Jackson reported to Portsmouth that Albacore exceeded expectations in every category of basic seamanship and control. The real test came next: high-speed submerged runs designed to determine whether the Teardrop hull could deliver the dramatic performance improvements predicted by the model basin tests. This was the moment that would validate or destroy years of research, millions of dollars in investment, and the careers of everyone who had championed the radical design. If Albacore couldn't significantly exceed the speeds achieved by conventional submarines, the entire experimental program would be judged a failure and the Navy would return to traditional hull forms for all future construction. The test was scheduled for October 14, 1953, conducted in deep water far enough from shore to avoid commercial shipping, but close enough to allow rapid return to port if problems developed. Weather conditions were nearly perfect: calm seas, moderate winds, excellent visibility. Albacore dove to test depth, leveled off at 150 feet, and began accelerating under maximum power from her diesel-electric propulsion system. Inside the submarine, engineers monitored dozens of instruments simultaneously, recording pressure readings, vibration levels, acoustic signatures, power consumption, control surface angles, trim adjustments, and 100 other variables that would be analyzed later to understand exactly how the hull performed. The crew felt the submarine surge forward with a smoothness that was completely unlike the rough, straining acceleration of traditional boats. There was no shuddering as the propeller bit into the water, no cavitation noise from turbulent flow over poorly streamlined surfaces, no sense that the vessel was fighting against the water rather than moving through it. Instead, Albacore seemed to glide, almost effortlessly, cutting through the ocean with a grace that felt more like flying than sailing. The helmsman reported that steering remained responsive and precise, even as speed increased. Conventional submarines often became difficult to control at high speeds, as flow turbulence disrupted rudder effectiveness. But Albacore's smooth hull eliminated most of that turbulence. The speed indicator climbed steadily: 15 knots, 20 knots, 25 knots. Engineers exchanged glances, checking and rechecking their instruments, worried that something had malfunctioned or that they were misreading the data. But the readings were consistent across multiple independent systems. Albacore was already moving faster than most World War II fleet submarines could achieve on the surface, and she was still accelerating. At 28 knots, some engineers expected performance to plateau as the propulsion system reached its limits, but the speed continued to increase. 30 knots, 32 knots, and finally, 33 knots, a speed that shattered every existing record for submerged operations and exceeded what most surface vessels could achieve. Captain Jackson immediately ordered additional verification runs to ensure the results weren't a fluke or measurement error. Albacore slowed, turned, repositioned, and made the high-speed run again. The results were identical: 33 knots, sustained for several minutes without difficulty, with power consumption actually lower than what conventional submarines required to reach 20 knots. The implications were staggering. Albacore wasn't just a little faster than traditional submarines. She was almost twice as fast while using significantly less power and generating far less noise. The destroyer escorts assigned to monitor the trial and provide safety support found themselves unable to keep up. Their sonar operators reported that contact with Albacore had been lost completely during the high-speed runs. The submarine simply disappeared from their screens, moving too fast and too quietly for their equipment to track effectively. When Albacore surfaced after the trials, the destroyer captain radioed congratulations mixed with concern. noting that if this performance was typical of modern submarines, his anti-submarine warfare systems were obsolete. Back at Portsmouth Naval Shipyard, the data was compiled, verified, and packaged for immediate delivery to Navy headquarters in Washington. Captain Jackson included a cover memo that understated the magnitude of the achievement in the dry language typical of official Navy communications. But his conclusion was unambiguous. USS Albacore had demonstrated performance characteristics that exceeded the most optimistic predictions of the design team and represented a fundamental breakthrough in submarine technology. The teardrop hull concept was validated beyond any reasonable doubt. When the data package reached Admiral Hyman Rickover's office, he reportedly stared at the numbers in silence for several long minutes, before ordering his staff to conduct a complete independent verification. Rickover, known for his brilliant engineering mind and his absolute intolerance for error or exaggeration, couldn't believe that a diesel-electric boat using relatively modest power had achieved speeds that his nuclear submarines were expected to reach years in the future after enormous investment and development. He demanded that the instruments be recalibrated, that the trial be repeated under controlled conditions with Navy observers present, that every possible source of error be eliminated before he would accept the results. The verification trials were conducted 3 weeks later with Rickover's representatives aboard and additional monitoring equipment installed. The results were identical. USS Albacore could sustain 33 knots submerged, could maintain that speed for extended periods, could maneuver effectively at high speed, and did all of this more quietly and efficiently than conventional submarines running at half that speed. Rickover immediately understood the implications. Every submarine under development in the United States, including his own nuclear boats, was using the wrong hull design. If Albacore's performance was real and replicable, then the entire American submarine fleet was functionally obsolete before most of the boats had even been built. Emergency meetings were called at the highest levels of Navy command. Design teams working on the Skipjack-class nuclear attack submarines were told to stop work immediately and redesign the hull using Albacore's teardrop configuration. The George Washington-class ballistic missile submarines, intended to carry America's nuclear deterrent beneath the seas, underwent similar radical redesigns mid-development. Shipyards from Connecticut to California received urgent orders to retool their facilities for the new hull form. Engineers scrambled to recalculate internal arrangements, ballast tank configurations, equipment placements, and 1,000 other details affected by the change from traditional to teardrop hulls. Billions of dollars in contracts were rewritten. Years of engineering work were discarded. Production schedules were disrupted. Training programs had to be modified. Technical manuals required complete revision. The entire trajectory of American submarine development pivoted in a matter of weeks based on the data from a single experimental boat that most officers had dismissed as a waste of money just months earlier. The transformation was expensive, disruptive, and controversial, but the performance advantage was too great to ignore. Any submarine built with a conventional hull would be hopelessly outclassed by boats using Albacore's design. The transformation wasn't just about speed. As engineers analyzed Albacore's performance data in detail, they discovered that the teardrop hull delivered benefits across every dimension of submarine operations. The dramatic reduction in drag meant the boat could operate at high speeds, using significantly less power, which translated directly into extended range and endurance. A diesel-electric submarine could patrol longer before needing to surface for battery recharging, while a nuclear submarine could maintain higher average speeds without straining the reactor. The smooth flow of water over the hull eliminated the turbulence that generated noise, making Albacore significantly quieter than conventional submarines, even when moving at maximum speed. Acoustic testing showed that Albacore at 30 knots generated less noise than a conventional submarine at 20 knots, a revolutionary improvement that would make detection far more difficult for enemy sonar. The wide midsection provided more internal volume for equipment, weapons, and crew spaces than traditional narrow hulls, allowing designers to fit more capabilities into a given length of submarine. The tapered ends improved maneuverability, allowing tighter turns and faster depth changes by reducing the moment of inertia around the submarine's center. Albacore could reverse course in roughly half the turning diameter required by conventional boats, a critical advantage in tactical situations. The symmetrical shape front and rear meant that flow remained attached to the hull more effectively across a wider range of speeds and angles, reducing the risk of control problems that plagued conventional submarines when maneuvering aggressively. In every measurable category — speed, efficiency, maneuverability, acoustic signature, internal volume, depth control — the Teardrop design was superior to conventional configurations. The magnitude of the advantage was so substantial that it fundamentally altered the strategic calculus of submarine warfare. American submariners would enter any conflict with a technological edge so pronounced that it approached decisive superiority, assuming all other factors remained equal. But while American engineers celebrated their breakthrough and scrambled to incorporate it across the entire fleet, Soviet naval intelligence was beginning to piece together fragments of information that would eventually trigger a crisis in Soviet submarine development. The first reports reaching Moscow were fragmentary and confusing. Photographs taken by intelligence trawlers showing an unusually shaped American submarine at Portsmouth. Intercepted radio traffic mentioning speed trials and hydrodynamic testing. Debriefings from Soviet naval attachés who had observed Albacore entering and leaving port during diplomatic visits. The intelligence was incomplete and difficult to interpret, but it was clear that the Americans were testing something unconventional. Initial assessments from Soviet submarine designers and naval architects were dismissive and sometimes openly mocking. The teardrop shape violated established principles of submarine design that had been developed over decades and validated through extensive Soviet testing and operational experience. Soviet hydrodynamic theory, based on German U-boat research from World War II and refined through years of Soviet experimentation, predicted that a submarine with a wide midsection and tapered ends would be unstable, difficult to control, prone to rolling in rough seas, and unable to match the performance of properly designed submarines with traditional hulls. One senior Soviet naval architect, Yuri Kormilitsyn, who had designed several classes of Soviet submarines and was considered one of the nation's leading experts, wrote a classified assessment that would later become infamous after the Cold War ended and Soviet archives were opened. He analyzed the limited intelligence on Albacore and concluded with complete confidence that American claims about the vessel's performance were either deliberate propaganda intended to deceive Soviet planners and waste their resources on dead-end designs, or the result of measurement errors and wishful thinking by American engineers who didn't understand hydrodynamics as thoroughly as their Soviet counterparts. Kormilitsyn's memo predicted that operational testing would reveal serious flaws. The teardrop hull would prove unstable in operational conditions, difficult for crews to control during tactical maneuvers, vulnerable to damage from the structural stresses created by its unconventional shape, and ultimately incapable of matching the performance of Soviet submarines that used proven traditional designs. He recommended that Soviet submarine development continue along established lines, and that intelligence resources not be wasted attempting to steal secrets about Albacore, because the American design was clearly a failure not worth copying. The memo was circulated widely among Soviet submarine designers, fleet commanders, and party officials responsible for naval development, and it helped establish a consensus that Albacore represented American engineering hubris rather than a genuine breakthrough, another example of American tendency to pursue expensive novelties instead of refining proven concepts. That comfortable consensus began to crack as operational reports from Soviet submarine commanders started arriving in Moscow throughout 1954 and 1955. A captain operating in the North Atlantic with one of the Soviet Navy's newest boats reported an encounter with an unidentified American submarine that he initially trailed successfully at moderate speeds. When the American boat detected the pursuit and accelerated, the Soviet captain increased his own speed to maintain contact. But the American submarine pulled away effortlessly, accelerating to what the Soviet captain estimated as impossible speed, certainly over 30 knots submerged, possibly faster. His sonar operator lost contact completely within minutes. The Soviet boat, running at maximum speed and straining its propulsion system, was left behind without hope of reacquisition. Another commander, operating near the American coast on an intelligence-gathering mission, described attempting to trail what he believed from the unusual acoustic signature was USS Albacore. His boat followed the American submarine for several hours, maintaining a cautious distance to avoid detection. When the American boat apparently detected the Soviet presence and took evasive action, the Soviet commander attempted to close the distance and regain contact. What happened next was humiliating. Albacore simply vanished from sonar, accelerating away at a speed that left the pursuing Soviet boat struggling futilely in her wake. The Soviet commander's report concluded with the uncomfortable admission that present equipment is inadequate for trailing modern American submarines if they employ maximum speed for evasion. Multiple patrol reports from different commanders in different ocean areas mentioned similar encounters. American submarines with unusual acoustic signatures that could accelerate to unprecedented speeds when pursued, leaving Soviet boats unable to maintain contact no matter how aggressively they pushed their own propulsion systems. The pattern was clear and consistent, and it directly contradicted the engineering assessments that insisted such performance was impossible or propaganda. Soviet naval intelligence attempted to reconcile these troubling field reports with the technical assessments that insisted Albacore's performance claims were exaggerated or false. Some analysts suggested that the Americans had secretly installed nuclear reactors in Albacore and were deliberately lying about her diesel-electric propulsion to conceal a new reactor design. This theory gained some traction because it seemed to explain the performance reports without requiring Soviet engineers to admit their hydrodynamic theories were wrong. If Albacore had massive power from a secret reactor, perhaps even a flawed hull design could achieve high speeds through brute force. Other analysts proposed that the speed reports from Soviet commanders were simply mistakes, that acoustic conditions, thermal layers, or other ocean phenomena were creating false impressions of American submarine speed and position. A few suggested that the entire Albacore program might be an elaborate deception operation, with the Americans deliberately leaking false performance data through channels they knew Soviet intelligence monitored, hoping to trick Soviet designers into pursuing a dead-end teardrop design, while American submarines actually used completely different technology. But as months passed and the pattern of reports continued from multiple independent sources, denial became increasingly difficult to maintain. Soviet submarines were being consistently outrun by American boats during encounters in the Atlantic, Pacific, and Arctic. Patrol commanders who had decades of operational experience and whose professional competence was beyond question were submitting frustrated reports describing the humiliation of watching American targets escape at speeds their boats simply couldn't match. Training exercises simulating attacks on American surface forces had to incorporate new assumptions about submarine performance. Soviet attack boats would be unable to intercept American reinforcements if American submarines could establish protective screens while running at speeds Soviet boats couldn't match. The strategic implications were dire and getting worse. If American submarines could move at 30 knots or faster while running quieter than Soviet boats at any speed, they would dominate every underwater encounter, able to strike at will while remaining effectively invulnerable to pursuit or counterattack. The crisis finally reached Admiral Sergei Gorshkov, Commander-in-Chief of the Soviet Navy and one of the most powerful and feared military figures in the Soviet Union. Gorshkov had risen through the ranks through a combination of political skill, strategic vision, ruthlessness towards subordinates, and absolute commitment to building a Soviet Navy capable of challenging American naval supremacy worldwide. He was known for his intolerance of failure, his willingness to destroy careers of officers who disappointed him, and his determination to accept no excuses when Soviet capabilities fell short of requirements. When the accumulated intelligence on Albacore and the field reports from submarine commanders reached his desk, Gorshkov ordered an immediate and complete reassessment, making it clear that he expected answers rather than theories, and that the careers of everyone involved would depend on providing him with accurate information rather than comfortable lies. The meetings that followed were tense, confrontational, and sometimes brutal. Design Bureau. Chiefs who had confidently predicted Albacore's failure just months earlier now faced uncomfortable questions about why their theories were being systematically disproven by operational reality. Why were Soviet submarines being outrun if the American design was flawed? Why were multiple experienced commanders reporting the same impossible speeds if the reports were errors? Why had Soviet hydrodynamic theory failed to predict that teardrop hulls would work? The questions came with implied threats. Failure to provide satisfactory answers would result in removal from positions, loss of privileges, possibly worse consequences. Under this intense pressure, Soviet engineers reluctantly began conducting their own water tunnel tests using scale models of teardrop-shaped hulls. The work was done quietly, without fanfare, because admitting that American designs needed to be tested implied that Soviet theory might be wrong. A dangerous admission in an environment where professional competence and political loyalty were inextricably linked. But the results of these secret tests were shocking and professionally humiliating for the engineers involved. The American teardrop design actually worked exactly as claimed. The hull form dramatically reduced drag compared to conventional submarine shapes, enabling higher speeds with significantly less power. The smooth contours improved maneuverability and reduced noise generation. Everything that Soviet submarine doctrine had taught for decades about proper hull design was simply wrong. The Americans, through systematic experimental testing, had discovered something fundamental about hydrodynamics that Soviet theorists, despite their confidence and expertise, had completely missed. Gorshkov faced a nightmare scenario that combined military crisis with political danger. The Soviet Union had invested billions of rubles over years in submarine construction programs that were now revealed to be technologically inferior before the boats even entered operational service. Dozens of submarines were under construction in shipyards across the Soviet Union, using hull forms that would make them slower, noisier, less efficient, and less capable than American boats. Production facilities had been designed and built, tools and fixtures manufactured, workers trained in specialized skills, supply chains established to provide materials and components, all for designs that now needed to be abandoned or drastically modified. The political consequences of admitting such a massive miscalculation to party leadership were potentially catastrophic. Resources had been allocated, 5-year plans constructed, commitments made based on assumptions that were now proven false. Heads would roll, literally or figuratively, when the magnitude of the failure became known. But the military consequences of continuing with inferior designs while the Americans pulled further ahead were even worse. Soviet submarines would enter any future conflict at a decisive disadvantage, outmatched in the key characteristics, speed, stealth, endurance, that determined success or failure in submarine warfare. After consultation with his senior staff and careful political calculation about how to present the situation to party leadership, Gorshkov made a fateful decision. The order went out across the entire Soviet submarine construction enterprise: stop work on all submarines using conventional hull designs and transition immediately to teardrop configurations based on the American Albacore model. The November-class nuclear attack submarines, already partially built with millions of rubles invested, were to be redesigned mid-construction, with hull sections already welded together, cut apart, and modified to incorporate teardrop profiles. Design bureaus received instructions to develop Soviet versions of the teardrop hull and rush them from drawing board to production as quickly as possible, cutting corners on testing if necessary to compress the normally years-long development process. It was one of the largest and most expensive course corrections in Soviet naval history, driven entirely by the demonstration provided by a single American experimental submarine that Soviet experts had confidently predicted would fail. But the forced adoption of the teardrop hull exposed deep structural problems in Soviet submarine development processes and capabilities. American engineers aboard Albacore had spent years systematically refining the design, testing dozens of variations, learning through careful experimentation what worked and what didn't, building a detailed understanding of how every aspect of the hull interacted with every other aspect. They had discovered through trial and error how to arrange ballast tanks to maintain proper trim, where to position control surfaces for optimal effectiveness, how to design propeller systems that worked efficiently with the teardrop shape, what internal arrangements maximized both capability and crew habitability. Soviet designers were attempting to copy the final result without understanding all the incremental lessons that had led to it. They had stolen photographs showing the external shape, but no detailed internal arrangements. They had intelligence reports describing performance, but no engineering data explaining how that performance was achieved. They were trying to reverse engineer a complex system while under intense time pressure and political threats, without the freedom to fail and learn that American engineers had enjoyed. The result was predictable. Soviet implementation of the teardrop hull encountered a cascade of problems that American engineers had already solved years earlier through systematic testing. Soviet designers struggled with stability and control issues. The wide midsection that made the teardrop hull efficient also created different buoyancy and stability characteristics that required carefully designed control systems and thoughtful arrangement of ballast tanks and trim systems. Soviet engineers, working from incomplete information and under deadline pressure, made decisions that seemed reasonable on paper, but created operational problems in practice. Their boats had tendencies to roll in certain sea states, required constant attention from helmsmen to maintain proper attitude, experienced difficulty recovering from certain maneuvers. They encountered unexpected difficulties with internal arrangement and space utilization. Fitting all the necessary equipment, weapon systems, crew spaces, and machinery into the unfamiliar teardrop shape proved far more challenging than traditional hull arrangements. Soviet submarines ended up more cramped than intended, with less efficient use of internal volume than American designs achieved. Equipment access was awkward, maintenance was difficult, crew habitability suffered. They discovered that propeller and propulsion designs optimized for conventional hulls didn't work efficiently with teardrop shapes. The flow patterns around the stern were completely different, requiring new propeller designs, different shaft configurations, modified thrust-bearing arrangements. Soviet engineers had to essentially reinvent submarine propulsion systems, and their initial attempts were crude and inefficient compared to American solutions that had been refined through years of testing aboard Albacore. Most critically and embarrassingly, Soviet teardrop submarines were dramatically noisier than their American counterparts. The rushed development process had prioritized getting boats into production quickly rather than optimizing acoustic performance. Hull design decisions that seemed reasonable from a purely hydrodynamic standpoint created structures that transmitted machinery noise efficiently into the water. Equipment mounting systems that were adequate for conventional hulls proved inadequate for teardrop configurations, where the hull shape itself acted as an acoustic resonator. Propellers designed hastily without extensive testing cavitated badly at certain speeds, creating noise signatures that could be detected for tens of miles. The result was a generation of Soviet submarines that looked superficially similar to American skipjack-class boats, but performed significantly and sometimes dramatically worse. Soviet November-class nuclear attack submarines were faster than their predecessors and represented an improvement over conventional designs, but they were still slower than American skipjack-class vessels, less maneuverable, far noisier, less reliable, and more difficult for crews to operate effectively. The performance gap that Soviet leadership had hoped to close by copying American designs remained wide and in some respects actually increased as American submarines continued to evolve and improve while Soviet boats struggled with the basic challenges of making the teardrop configuration work properly. the noise disadvantage was particularly damaging both militarily and psychologically. American sonar operators using increasingly sophisticated passive detection systems could hear Soviet submarines at ranges where the Soviet boats had no hope of detecting their American counterparts. American attack submarines could track Soviet ballistic missile boats throughout their patrol areas, maintaining contact continuously while remaining undetected themselves. In exercises and simulated combat scenarios, American submarines consistently achieved overwhelming kill ratios against Soviet opposition. The technological superiority established by USS Albacore's demonstration had translated into operational dominance that would persist throughout the Cold War. The performance gap drove Soviet submarine commanders to frustration, anger, and sometimes desperation. These were professional naval officers, many with decades of experience, now forced to operate boats that they knew were inferior to American designs. One November-class captain, after a NATO naval exercise where his brand-new submarine was repeatedly detected, tracked, and simulated killed by older American skipjack-class boats, wrote a bitter classified memo stating that "We are sailing obsolete boats against an enemy that has already won the technology race before we could even enter it properly. Present equipment is inadequate for assigned missions and places crews in unacceptable risk in any realistic combat scenario." Another commander, ordered to trail an American Ohio-class ballistic missile submarine on patrol, reported in frustration that contact was established briefly, then lost permanently when target accelerated. Pursuit attempted at maximum speed, but reacquisition proved impossible. Present capabilities are fundamentally inadequate for strategic surveillance missions. The memos accumulated in Moscow, documenting a technological defeat that Soviet propaganda could never acknowledge publicly, but that operational reality made impossible to ignore or deny. Meanwhile, USS Albacore continued her remarkable experimental career, undergoing modification after modification as American engineers systematically pushed the boundaries of submarine performance and explored possibilities that the original design had opened. In 1956, she underwent her first major refit, emerging with contra-rotating propellers, two propeller assemblies mounted on concentric shafts spinning in opposite directions. The system was mechanically complex and required sophisticated engineering to implement, but the benefits were substantial. Contra-rotating propellers cancelled out torque effects that caused submarines to pull to one side during acceleration, improved efficiency by recovering energy from the rotational flow behind the forward propeller, reduced vibration that could be transmitted through the hull as detectable noise, and increased overall thrust. The system worked brilliantly in testing, and within years, it was being incorporated into operational American submarines, where the performance benefits justified the additional mechanical complexity. In 1961, Albacore received another radical modification: experimental stern planes arranged in an X configuration instead of the traditional cross pattern where horizontal and vertical control surfaces met at right angles. The X configuration positioned 4 control surfaces at 45-degree angles, and the unconventional arrangement offered several advantages that weren't immediately obvious. It provided redundancy. If one control surface failed, the submarine retained full control authority because each surface contributed to both depth control and roll control. It reduced flow interference. The surfaces were positioned to minimize the wake effects, each created for the others. It improved effectiveness at extreme angles. When a traditional submarine pitched or rolled aggressively, some control surfaces became partially ineffective, but X-configured surfaces maintained authority across wider envelopes. And it reduced acoustic signature. The arrangement minimized cavitation and flow noise compared to traditional configurations. Testing demonstrated that the X configuration dramatically improved depth control precision, reduced control surface activity required to maintain trim, and enhanced maneuverability at all speeds. In 1965, Albacore underwent perhaps her most exotic modification, coating with a special polymer skin designed to reduce drag even further by minimizing turbulence in the boundary layer, where hull meets water. The polymer coating was applied in a thin layer over much of the hull, and it functioned by absorbing small-scale turbulent fluctuations before they could grow into larger eddies that created drag and noise. The technology was difficult to implement. The polymer had to adhere properly to the hull, maintain its properties across the temperature ranges and pressures submarines experienced, resist degradation from seawater, and survive the stresses of normal operations. Early versions failed repeatedly, peeling off or degrading too quickly to be practical. But eventually, American engineers developed formulations that worked reliably, and the drag reduction, while modest compared to the improvement from the teardrop hull itself, was measurable and valuable. Each innovation underwent exhaustive testing aboard Albacore before being incorporated into operational submarines. Each failure was carefully analyzed, with lessons learned documented and applied to subsequent development efforts. The crew serving aboard Albacore throughout these years became accustomed to constant change, installing new equipment during shipyard periods, running endless test trials to evaluate modifications, providing detailed feedback to engineers who treated their observations as valuable data rather than complaints or criticisms. It was unglamorous, demanding work that rarely received public recognition, generated no dramatic headlines, earned none of the glory associated with combat operations or record-breaking achievements. But this systematic experimental work was building the foundation for American submarine superiority that would last for generations. Every innovation tested aboard Albacore, every problem identified and solved, every lesson learned through trial and error represented knowledge that couldn't be stolen through espionage or reverse engineered from photographs. It was tacit knowledge, encoded in engineering practices, design philosophies, test procedures, and accumulated experience that took years to develop and couldn't be easily transferred or replicated. The influence of USS Albacore spread far beyond the United States Navy. British naval designers, receiving detailed intelligence about American submarine developments through NATO intelligence sharing agreements and the special relationship between American and British naval establishments, recognized immediately that the teardrop hull represented a breakthrough they needed to adopt. British Valiant-class nuclear submarines, entering development in the late 1950s, incorporated teardrop hulls derived from Albacore's design, combined with British nuclear reactor technology. French engineers, working more independently but aware of American achievements, incorporated teardrop configurations into their Rubis-class attack submarines, developing their own variations adapted to French operational requirements and construction capabilities. Even the Chinese, receiving limited intelligence through their own espionage networks and studying published photographs and unclassified technical literature, began developing submarines with Albacore-inspired shapes in the 1970s and 1980s as their submarine construction program matured. By the end of the Cold War, virtually every submarine being built anywhere in the world used some variation of the teardrop hull that Soviet engineers had once dismissed as impossible, and American engineers had validated through the systematic experimental program centered on USS Albacore. In 1972, after 19 years of experimental service that had seen her undergo more major modifications than most submarines experienced in entire operational careers, USS Albacore was finally decommissioned. The decision reflected not any failure or inadequacy of the vessel itself, but simply the reality that her mission had been accomplished, and that newer, more sophisticated test platforms with better instrumentation and more advanced propulsion were available for continuing experimental work. By 1972, everything Albacore could teach had been learned, everything she could test had been tested, every innovation that her design made possible had been explored and either validated or disproven. She had never fired a torpedo in combat, never tracked an enemy vessel in wartime, never participated in the dramatic submarine operations that filled movies and novels and captured public imagination. By traditional measures of military service, by the metrics used to evaluate combat vessels and award decorations, her career had been completely uneventful, 19 years of repetitive testing, endless trials, routine operations that generated no excitement and earned no recognition beyond small technical communities. But by any rational measure of impact, by any serious assessment of contribution to national security and naval warfare, USS Albacore was the most influential submarine in history, more important than any record-breaking boat, more consequential than vessels that sank dozens of enemy ships, more revolutionary than submarines that conducted dramatic special operations or strategic patrols. Every modern submarine, from American Virginia-class boats costing billions of dollars each to Russian Yasen-class vessels, representing the pinnacle of Russian submarine technology, to Chinese-type 093 submarines, representing China's growing naval capabilities, uses technologies, design principles, and operational concepts pioneered aboard this unarmed research vessel, built for testing rather than fighting. The story of USS Albacore and the Soviet response to her development illustrates fundamental truths about technological competition, military innovation, and the nature of strategic advantage in a world where conflicts are won or lost based on capabilities developed years before battles are fought. American superiority came not from superior resources, though America's industrial capacity helped, and not from superior theoretical knowledge, because Soviet engineers were highly educated and scientifically sophisticated. American superiority came from systematic experimentation, institutional willingness to challenge established assumptions, cultural acceptance that failure during testing was valuable rather than shameful, and intellectual humility to accept empirical data that contradicted theoretical predictions. Soviet engineers initially failed not because they were incompetent, but because they trusted their theories more than they trusted reality, because institutional pressures punished admission of error, because political and professional consequences of being wrong created incentives to deny evidence rather than revise understanding. The same scientific and engineering talent that achieved remarkable Soviet successes in areas like rocket development and space exploration produced inferior results in submarine development, because the organizational and cultural context was different. Today, USS Albacore sits as a museum ship in Portsmouth, New Hampshire, preserved as a National Historic Landmark next to the shipyard where she was built nearly 70 years ago. Visitors can tour her cramped interior, see the experimental equipment that changed naval warfare, touch the hull that proved the teardrop concept worked, and learn about the crew who served aboard her and the engineers who designed and modified her throughout her long experimental career. The submarine rests on dry land now, her testing days long over, her engines silent, her instruments removed or no longer functioning. But her legacy continues beneath the world's oceans in every submarine that glides through the depths using the shape and principles she validated. The radical has become normal. The experiment has become doctrine. The mockery has become universal adoption. And the submarine that hit 33 knots when everyone said it was impossible changed the course of naval history and humbled a superpower without firing a single shot in anger.